Hi, everyone. Welcome to the WiM webinar. This is our second time of our webinar series presented by women in MICCAI on the topic of health equity in the AI era, a humanistic approach to fair and equitable medical AI. Today, we are very honored to have Dr. Maria Zuluaga to be our speaker today. And her topic will be on building trustworthiness through robustness, a topic that is very timely and important for our medical AI world today. Before we start and dive into the talk, I want to take maybe 2 or 3 minutes to talk about WiM. WiM is a committee as part of MICCAI where we strengthen and widen the representation of female researchers and scientists. But we do not only welcome female researchers and scientists to join our events and activities. We welcome people from all gender or background to work together to support and build this community. And in the past MICCAI, which just happened about 2 months ago, we presented multiple events and awards, including this one signature event called Women MICCAI Launch Event, where we have panel discussion and we provide the lunch boxes. And we also have our scientist designed WiM gifts presented to all the attendees if you come early enough. And then we have 2 awards, which is the WiM Best Oral Presentation Award and WiM Best Health Equity Paper Award. And this is the memory of our WiM launch event where we have a full room, and it's actually more than a full room. So next time we will try to book a larger room if possible. And we have all those panelists, including Dr. Maria Zuluaga, who will present today. And these are the award ceremony moments for our WiM awards, including the Health Equity Award and the Best Oral Presentation Award. And those awardees will also be our speakers and panelists in our future WiM webinars to share their experiences in working on health equity research and how to present research papers orally. So you can see we had our first webinar talk by Dr. Carrie McInerney from Cambridge in June, and this is our second webinar. And on January 23rd, 2025, we will have our Best Health Equity Paper winners presenting on how to conduct health equity research. And with the joint effort of WiM and the MICCAI steering committee and all the members from the MICCAI organization leadership board, we also made an effort to provide childcare cost reimbursement and connect with the on-site childcare services at Marrakesh this year. So this is also one effort we want to promote further in our future MICCAI meetings. And something exciting is for our MICCAI board, we now have 13 members with 5 newly elected board members, which are highlighted in red. And together, we want to work with you to serve the community and to make our women researchers more prominent and highlight their work. And we also have a number of social media, including X or Twitter, Facebook, and LinkedIn. And something new I want to emphasize is from this year, we are going to build a WiM virtual community through Slack, because we found Slack is one of the ideal platforms where we can talk to each other, like a post announcements about the recent events, and also build a small community within focusing on special topics. And I also want to promote the connection between the members of WiM so that we have a family online. And whenever people go to different conferences, for example, in Europe this week, you can call for people to like a meetup at Europe where you are a member of WiM or you want to be a member of WiM. And I think we may post something very soon this week. Okay, without further ado, I will give the stage to Wina so she can introduce the speaker.
Yes, thank you, Robo, for your introduction. I'm very honored to introduce our invited speaker, Dr. Maria Zuluaga. Dr. Maria Zuluaga is a senior lecturer at the Data Science Department at EURECOM with an affiliation position with the School of Biomedical Engineering and Imaging Science and King's College of London. Her research team focused on the development of novel machine learning methods for multi-modal data that can be safely used to advance the healthcare research and improve clinical practice. From an application standpoint, her research work aimed to answer questions coming from cardiovascular and neurovascular imaging, as well as cancer research. So without further ado, let's welcome Dr. Maria Zuluaga to give us her invited talk.
Thanks a lot, WiM, for the introduction, and thanks, Robu, and all the MICCAI, women in MICCAI members, panel members or board members for the invitation. I'm really excited to be here. And so indeed, so the topic of my talk today is building trustworthiness through robustness. But before I get started, for those that do not know me, I'll give a brief introduction about myself, and just to break a bit the ice between us, I thought to introduce myself through all my MICCAI journey, which means starting from when I became a member of the MICCAI community until today, and see that through all along my career. So I come from Colombia, for those that don't know. So I did a master's degree there, and then by chance I moved to Australia for an internship at CSIRO, where the MICCAI 2007 took place. I left CSIRO just before MICCAI happened, but they were kind enough to keep me one of the, at the time they were giving some goodies as a souvenir of MICCAI, and I was able to keep their really beautiful handbag that they were giving at the time. After that, I moved to do my PhD in Lyon and at the Université de Lyon, and that allowed me to participate to MICCAI 2008, 9, and 10. I finished my PhD and moved just next door to Grenoble for a postdoctoral position at the synchrotron, and that's the time I joined MICCAI 2011 in Toronto. Then I moved to University College London, and I was that gave me the opportunity to go to MICCAI 2012. I missed 13, 14, 15, and 16, where I left academia, and I thought I was never going to be part anymore of the MICCAI community. I went to industry. So for those listening here that you don't know where to go, you can go to industry and come back and forth. It's possible. I can confirm. Then I came back to academia at EURECOM as an assistant professor, and that allowed me to again participate MICCAI. I was involved in the organization of MICCAI 2020 as a program chair, where we were hoping that we were bringing MICCAI for the first time to South America, but COVID arrived, and so we had 2 editions online. I attended back in person in Singapore 2 years ago, and I skipped the 2023 edition of MICCAI because I was in maternity leave, and this is why in the last edition I was able to join MICCAI with a new, very, very young member like that you see in the photo, which is my son. So that's me. So again, I'm an assistant professor at EURECOM right now with a joint affiliation at King's College London. Many of you have heard of King's College London, I suppose, but a bit less about EURECOM. So now let me give you a bit of context of where we are based. So this is Nice, and we are located here in the mountains next to the French Riviera, next to other institutes that are very well known in the MICCAI community, such as INRIA. So this is EURECOM, and this is how we look like. So what you should see there back in the photo is the sea. So we come to work in the morning in the mountains, and in the afternoon we get to enjoy the sea and the beautiful mountains. In terms of research, now starting to move into the talk. So what we're working with in my research group, we try to answer the following question is how can we build efficient, robust, and reliable methods that can be safely deployed for medical usage? For this purpose, we address 3 specific issues, which is the efficient use of data. In particular, we're interested in small sample sizes, which is something very relevant for the topic of this webinar, which is health equity. Robustness and reproducibility, trying to follow a human-in-the-loop approach, making use of medical images, and more recently, we try to combine them with wearable devices. And all of this to improve and assist medical decisions, very importantly for this, especially for this webinar, while achieving health equity. So what I try to show you for this talk is I'll try to show you and convince you that by developing efficient, robust, and reliable artificial intelligence methods and systems, we are at the same time building trustworthy AI methods and systems that will enable health equity. And what I'll try to show you over this talk is how this happens and how we are trying to make this happen. So to start with this, let's start with defining a couple of terms. So first of all, it's what is trustworthiness, because it's a term that is now very trendy and everyone has an opinion on it, so let's try to formalize it. So trustworthy, the term trustworthy AI gained a lot of prominence back in 2019, thanks to an initiative of the European Union that they developed the ethics guidelines for trustworthy AI. And here, although it was like, it boosted the use of the term, in the end, it's underlying a lot of concepts that are about building reliable, fair, and ethical AI systems, which have been discussed along the years. So in these guidelines, they highlight 7 core principles of trustworthy AI. The first one is human agency and oversight, which is the fact that we have some stakeholders that are the final users of these AI systems, and they should be checking that things are working well. Technical robustness and safety, which is what brings us today. Privacy and data governance, which means my data is used for an AI system or I'm being processed through an AI system, but my data should be protected. Transparency, which is if something is happening in this AI system, I have the right to know what is going on. Diversity, non-discrimination, and fairness, which is about not having biases. And again, when we build an AI system, we would like to have access to all the possible data in the world to train our models, but as in practice, this is not possible. How we deal with these unrepresented groups so that like they can benefit from these AI systems. So societal and environmental well-being, which is if we develop these AI systems, they should be for the good of the society, for like for humans, without damaging the environment. And finally, accountability is like if the systems do something, who is responsible for them? And so what I'll try to show you here is that aside human agency and oversight, which is it's a task that is specific to the final users, to the stakeholders and the humans, all these other tasks are linked to technical robustness. And well, if you see in the graph, they are all linked to each other. But what our hypothesis, the thing that we're trying to push is like, what we consider is that by addressing technical robustness, we are in some way implicitly also covering some of the aspects on the remaining 5 principles. Okay, so now since we say tech robustness is the core, it's a core element to ensure trustworthiness, let's start by trying to define what robustness is, because there are loads of definitions similarly to trustworthiness, and we can find that at all levels, right? We have like definitions from the Oxford Dictionary to more like advanced scientific publications that provide definitions, and up to, as I illustrate in the figure in the image here, up to books that have like entire pages and pages trying to establish what robustness means. So very quickly, let's go through a couple of definitions. So the Oxford Dictionary says that is the ability to withstand or overcome adverse conditions or rigorous testing. In Wikipedia, we have a more extensive discussion of what it means, and they say that is the ability of a computer system to cope with errors during execution and cope with any erroneous input. We have the standards of the IEEE for software engineering, where they say it's the degree to which a system can function correctly in the presence of invalid inputs or stressful environmental conditions. And finally, this is one that I really like. It's from a research paper that appeared last year in Synthesis, which is the capacity of a model to sustain stable predictive performance in the face of variations and changes in the input data. One last definition that is more visual. So the authors propose a definition of robustness that encompasses other terms such as reliability and validity. And here they say that when we talk about reliability, it's the capacity of a model to be reproducible and replicable. So by reproducibility, they mean it will behave the same if we test on the same data, but not the same people that developed. If we replicate, it means we should be able to obtain similar results on different data sets. And validity refers to adversarial robustness. So it's if we have adversarial attacks, and external validity that they refer to out of distribution generalization. So all in all, if we combine all these definitions, we will see that there are some common elements to it that I try to summarize here. So we talk about variations in the inputs, that if we want to make them even more general, we can talk about specifications. So if we specify that we train an AI system in a certain way, and we talk here from the equipment to the data to the models that we use, our model is robust if any variations to these original specifications do not change the final performance of our system. Rigorous testing will be testing stress conditions just to make sure, again, that under variations of these original specifications, we will have sustained performance. And as a previous definition suggests, if something happens, these systems should be able to handle errors. So again, like what I'm trying to propose here is that trustworthiness is robustness. Is again, if we deal with robustness, we are advancing a lot in what regards building trustworthiness. So with the definition, the summary of the keywords that we just talked about, variations in specifications, rigorous testing and stress conditions, and sustained performance, and handling errors, we can revisit these principles that we first checked just to show you that indeed there is a direct link between all those principles and robustness. So again, in technical robustness and safety, we want to have sustained performance when there are changes in our original specifications. So if we look at one of the first principles, which is accountability, which is what happens if this AI system makes a mistake. So what we're talking is we should be able to audit our systems. And so if we develop robust systems that are able to handle errors when something happens, we are providing the capacity to be auditable and hence accountable. Then the second principle is about diversity and fairness, to give unbiased solutions for any group that might not be represented in the original training set. So we're here talking about changes in our original inputs. So we are dealing again with variations in the original specifications, which is a subject like that concerns technical robustness. Again, if we go to now the next principle, which is privacy and governance. So here we can think of how robustness intervenes in terms of malicious attacks that they might want to infer some information about the users. And here, so we are talking about these malicious attacks usually come very often in modifications to the inputs that will put the system into stress conditions where if we address robustness properly, we should be able to cope for. In terms of transparency, we need to figure out what is going on in these AI systems. And in particular for healthcare, this is going to be very important when there's something that is not going well. I take a lot of inspiration from one of the clinicians I first worked with in my career. At the time, I was at University College London. So I used to spend a lot of time in trying to make my model be perfect. And one day he told me, no, Maria, look, if your model fails, I'm fine with it as long as this model is able to tell me that something is going wrong. And here we talk about explainability. And so if we develop methods that can tell the user that something is going wrong, we are enabling transparency again through the property of robustness, which is being able to handle errors. And finally, on societal and environmental well-being, I mean, this is a very broad concept, but what it concerns to robustness is, again, let's remember that when we talk about specifications, we are talking about the capacity of having any change in the original training scenario. And so here, usually what we find where the state of the art is in very wealthy institutions, countries, etc., that have access to very powerful machines. So we should be able to develop robust methods that should be able to perform well even when we don't have such powerful equipment. So again, we will be trying to address environmental well-being and societal well-being to give access to everyone, again, related to health equity, by being robust to variations, again, in terms of the equipment we can use. And again, here we are talking about the first point of what we defined as robustness, which is variations in the specifications. So, hoping I have convinced you about this link, a very tight link between robustness and all the principles of trustworthiness. What we are doing in my research group is to build AI systems that are robust. This means that they will have sustained performance under stress conditions and rigorous testing. But up to here, I've not told anything particularly new. I'm very sure that most of the people online are also aiming at that. So just to bring some specificity to what we do, we are very interested in two specific cases of what all the big scope that I have just presented, that of what robustness is, which is first, varying input specifications. And here I'm interested on the data. So I'm very interested in what do we do if the properties of the data we use for training are changing. So indirectly, again, we are addressing the principle of diversity and fairness. And second, we are interested in variations in the equipment. Again, we are interested in seeing if we can find solutions that don't require huge amount of resources to be able to put in place. And here we're indirectly addressing the principle of societal and environmental well-being. The second aspect that we are very interested, which is focuses on the output of the models, is how do we handle errors? When we have a prediction, how do we know if the model is working? I mean, if it gave us what we expected for it to do. So here again, we are talking about accountability, because we should be able to detect performances that are suspicious, and we don't want to harm someone else. So to see what we do about that. And the second is, why is this not working? So to provide elements on transparency. Because this is the WiM seminar on health equity. For this talk, then I'll provide you some examples on the work that we have been doing regarding varying input specifications. I find handling errors is a bit out of the scope. So let's move into more detail of what it means, variations and changes in the input specifications. So the number of variations and changes we can have, it's huge. And this is because, especially as researchers, we develop method AI systems under, let's call it blue sky setup, where we think that everything is perfect in real life, and this is not the case. So here, I try to provide you with a table of what we usually assume at the development stage and what might happen in reality. So first of all, we assume that we have independent and identical distributions, and we will not have problems once our model is deployed in practice, but in reality, we will face distribution shifts. We assume that everyone has the capacity to label all the data that our models might need, but this is not the case in practice, where labels might be limited because they are very expensive, so they might be limited to a specific data set, but not to the large amount of resources that we might need. We also assume that we have large heterogeneous data sets, meaning that we have a lot of representativity, and then these are centralized, so we can access to all of them. But in reality, the data might be limited and might be across many hospitals. So having a centralized data set is challenging. And very related to that is that if they are scattered, then sharing is going to be very easy. But what we find more and more is that there are a lot of privacy concerns where we cannot move a data set from one place to another. The next point that we usually expect is that our data sets are clean, are properly acquired, are curated, and have all the information that we need. But what we find when we go to look at real-life clinical data sets, what we find is they are messy because they were acquired in the rush of clinical practice, so something is missing, and this might limit the usage that we have of the models that were developed in the blue sky setup. And again, we expect that everyone has the high-performing equipment that we use to develop our models. But in practice, what we have is very limited computational resources at hospitals or lower-income countries that might not be able to access what we have. So in the first part of this talk, I'll give you an example where we try to address the first 4 points, how we build models that are robust to distribution shifts, limited labels, and scattered data where we have privacy concerns. So to start, I mean, I think the topic of robustness to distribution shift has been is being largely studied in our community. I give here an example from the work of Maurice Fuchs, I hope I'm pronouncing it properly, where he illustrated some of the main causes of distribution shifts, such as concept drifts, population shifts, prevalent shift, malicious attacks, which is again linked to the problems of privacy, and acquisition shifts. So we try to see what could be a real case scenario in some of my recent work that could really involve a lot of these shifts in a practical scenario, and that indeed poses a lot of challenges to health equity. So let's suppose we have a couple of institutions anywhere in the world which are very interested in vessel segmentation, because we work a lot of vessel segmentation, but the issue is that one institution is working on the retinal vessels, another institution and many others are working instead on the brain vessels, and some others in the brain veins. But it happens that only institution one has the resources to obtain annotated data to develop a model. And you might think that this is not so realistic, like that it's very easy to obtain annotated data, but the reality is that the costs and resources required to curate and annotate datasets are non-trivial. And to illustrate that, I show here like some market analysis done by a company that the EMARC group did on how many people are using annotation services, right? I'm assuming, like, let's say doctors don't have, indeed in many places don't have the time because they need to be focused on the patient. So a hospital like outsources this practice. So what we see is that the big share of the market are in wealthier countries in North America and Europe. But when we have a look at areas of the world where like the income is lower, we see that the capacity to access to this type of services, it decreases. So it's not straightforward for every institution to have the internal resources to annotate data or have the money to pay an external company to do this. And even if they wanted, so let's say institution one is very happy to share their data, there's more and more restrictions regarding regulations and data policies that will not allow institution one to share what they have with the other institutions. So there are many works in the state of the art that try to like fulfill these limitations, such as like fine-tuning, assuming we have a model that someone might need to might want to share. We have strategies such as domain generalization, but it's not going to be suited to large domain gaps because, as I showed here, everyone might be working on a very difficult, they're all interested on the veins, but not on the same type of veins. So domain generalization might not be suited for this very large gap as we might observe in the vessels. We have foundation models that have been proven to be very powerful, but depend on very large centralized databases. And federated learning that will allow us to all these institutions to communicate among each other, but they will suffer from the fact that we have limited labels because only one institution has the labels, and client shifts because we have large domain gaps across institutions. And there's a recent approach to this, which is the federated domain adaptation, which tries to merge the concept of federated learning and domain adaptation into one. But it's very difficult to merge these two contexts because it involves very complex architectures. And in the end, we always need to retrain at the local target because it is just too complex. So what we try to do with my PhD student, Francesco Galati, recently is to try to an alternative that will find a midway between a foundation model and the domain adaptation at the local level. So what we proposed in a work that was recently presented at MICCAI in Marrakesh is to build a common latent representation of data from the various institutions. So here, each participant institution will allow for a federated training of a common latent representation. So we call it a data factory because we consider it will be too ambitious to call it a foundation model, as it's very specific and limited in size. And so through this, we should be able to learn a disentangled representation of the input data of each institution. And then at second stage, this richer and wealthier institution should be able to transfer the segmentation knowledge that it has, because it was able to acquire these data, annotate this data set that the other institution couldn't, to the other domains, to the other institutions, so that they can do their segmentation. And because we do this in a federated setup, we allow to keep both the data and the labels confidential. So there's no explicit sharing of the data from any of the institutions, so we address the problem of privacy. So a key aspect is, so we build this data, this common latent representation or data factory, again, and we have a common representation of the input data, but then we need to do the final segmentation. So the state of the art for this purpose has been for many years the cyclogram, where it allows us to translate an image from a given domain to another one. So here I think we are translating a tough MRI that shows us the arteries into a susceptibility weighted image that is going to show us the veins. That's what we want to do. The problem with the cycle gun is that when it performs this translation, these full translations might comprise spatial information, as we see in this example. What we had before becomes not like the zebra that we had here, starts to be a bit strange, and we lose a bit the shapes. And this might be acceptable for this kind of situations, but in sensitive applications like healthcare, preserving the shape and scale of each object is very, very critical. There have been specific approaches in healthcare applications to address the limitations of the cyclogram, but they heavily depend on adversarial training, which is very unstable to put into place, or they deal to very complex models, like very, very complex, which might be very prone to overfitting. So the solution that we proposed for this work was like to do simply a two-step approach to our solution. So what we first do is we train our data factory in an adversarial way so that it learns to disentangle the properties that describe an image. In this case, again, we were interested specifically, like in the example I presented, on the vessels, but we will go on the range from retinal vessels, which are 2D images, through 3D images of the arteries or the veins. So we need to disentangle aspects like intensity, like the location, because they are not in the same position, for example, for the brain and the brain arteries and the veins. The shape, because the size might change, and the density of them are also changed. So on the first step, we will disentangle this. And when we achieve this disentanglement in an adversarial way, we freeze the factory, which is what differs us from previous approaches. And we do a local adaptation that will allow us to learn the segmentation. And by avoiding this adversarial training, we avoid the risk of losing the shape consistency and scale consistency of our organs of interest, because when we are doing this adversarial training, somehow what we are trying to do is to fool the model. So we want our model to generate images that are as close as possible as the source or the target, but at the same time, we want to preserve shape and scale in the segmentation. So it's like indeed, as the name says, it's adversarial, but it takes the risk that if one preserves is more one of the two elements acting, it's stronger, then we will lose this shape and scale consistency. So we demonstrated our solution in 3 scenarios of increasing complexity, and by increasing complexity, which means larger domain gap. So we start with the simple scenario when we have 3 institutions with multiple scanners that are interested in segmenting the heart. So everyone is going to segment the same heart, just what changes is the scanner. We will segment left ventricle, right ventricle, and the myocardium. Then we move to a slightly more complex task where we have multi-modals called stripping of the brain. And we will have centers with PET images, CT, PD-weighted and T2-weighted MRIs. And finally, the most complex one, which is the one I presented at the beginning, we call it multi-organ, just because we're interested in the vessels in different locations in the human body. So we want arterial brain segmentation, for which we'll use TOF MRA, vein-brain segmentation, so they are very close to each other, but they are not the same, where we will use susceptibility-weighted images, and retinal vessel segmentation, where we'll use 2D OCTA images. So what we show here, I'll go very quickly in our results. So what we show is that we have, let's say, consistent good performance across all scenarios. We observe that where the gaps are not so large, simpler solutions like simply NNUNet, where you do a strong data augmentation, would work okay when you change the scanners. But as the gaps become larger and larger, and again, remember, we usually will have only one simulated institution with the annotations. What we will observe is that simpler methods just with data augmentation might not be as robust as before. And here just I present you a very quick visual example when we start from this source domain. So we have the TOF MRA of the brain arteries. And using this as the annotated domain, we are able to segment 2D OCTA retinal vessel images as we observe. So this is the corner I'm pointing here. I hope you can see my cursor presents the results we obtained, whereas competitor methods clearly fail on this. And here I present the ground. So just to summarize here, so here we achieve trustworthiness by being robust to potential lack of annotations. So we enable participants to benefit from richer resources, distribution shifts because we address population concept and acquisition drifts. We are robust to data heterogeneity because despite having varying organs of different like shapes and representations, we are able to preserve shape and scales, which is what we call the label preserving property. And we have rigorous testing because we are fostering reproducibility through open source code, and I invite you to try it if you are interested. Now let's move to the second part where I will talk about, I'll propose a solution for the problem where like our data in practice is not as neat as we would like, and that we might have varying, like we would like solutions that are cheap in terms of equipment. So to motivate this part of the talk, I look here at this is an example of what the new release of the ADNI dataset has. So we have loads of modalities, and ideally what you would like is that training and testing are the same. But what we might find in reality is something like this, that you developed a model with a lot of modalities, but in practice there will be few cases where they will have all of this to offer. How far are we from this to be a reality? Well, what I show here is the capacity, like the availability of PET-CT scans across the world. So what I show here is the amount of PET-CT scanners per million inhabitants. And what we see is that there are only very few places in the world where there's a high density of PET-CT scanners per inhabitant. And in most of the world, they are very scarce. So the possibility, for example, just for this example, that a model that considers PET-CT as part of the training data can be used elsewhere is very low, right? So this limits the worldwide impact of state-of-the-art models in healthcare and limits, again, health equity. So the current way to solve this is mostly through imputation-based methods, where we train a model to generate a fake image of the modality that is missing. So here I assume we didn't have we train a model with an MR and a PET, and so our imputation model should be able, given an MR input, to generate a synthetic PET, so that the multimodal model can be able to generate a prediction. The problem with this, which is something that my PhD student Awad Shabtoukaev has been studying, is that in certain cases, this synthetic data that we generate might cause these drifts in the distribution of the features. Here I illustrate the example with the heart disease data set, just to provide a very simple setting. But this might be like also the case in more complex data sets involving images, genetic data, etc. So we need to handle this with care, and we should not abuse of imputation, being able to know where to choose to use it or not. So what she developed and presented recently in the MMMI workshop, where she got the Best Presentation Award, is a multimodal learning that is designed to handle missing imaging modalities. It means if we don't have the PET image, we don't use it, but we don't generate a synthetic image for it. her solution, like, so what we propose as a framework is flexible because it can handle varying size data sets beyond the scenario of missing modalities. So I'll present a concrete example later. And it's end-to-end in that it eliminates the need to train very complex and computationally costly imputation models before being able to train a predictor. So with this, again, we are trying to address the problem of expensive equipment that might not be possible to use anywhere. So the core idea of this solution is to be able to learn from sets rather than from fixed size vectors. And for this, we make use of a permutation invariant architecture that allows us to operate on sets of modalities, again, rather than on specific vectors. And so this will relax the requirement of having fixed dimensional data. We achieve this then, so how we put this in place is to a two-stage training. So in a first stage, we will train our model with all the available images on our datasets. We assume we don't have any image modality, and we will encode the presence or absence of a modality through this variable M, okay? And so we will learn the relevant features by training our model first to predict what it wants to predict, I mean the final application, and to be able to reconstruct each of the modalities. Once our permutation invariant architecture is trained, we freeze it, and we pass to stage 2, where we will learn, we try to learn, so we will try to solve our prediction task with varying sizes. So here, what we will do is we start simulating the absence of a given modality. And so again, since we treat these as sets, we don't care if a missing modality is not, because what will happen is that if a given modality is missing, we simply remove it from the set, and there's not the problem of the fixed dimensional data that we used to have. We evaluate this in two use cases. The first one is Alzheimer's disease detection, where we work with the EDNI datasets, and we use T1 weighted MRs and PET images. And the idea is to be able to discriminate between cognitive normal and Alzheimer's disease. And we compare to two baselines of imputation models for missing modalities to generate synthetic images, such as PIX2PIX and the cycle GAN. And the second use case is about breast cancer classification, where we will use histopathological images of different magnifications. So again, here is not about missing modalities, but what I said, images of different sizes, because as the magnification changes, we will have vectors of different sizes. And what we use as baselines is two different CNNs that propose ways to average the predictions of each of the input images to obtain a final solution. And this, again, I want to remind you that this second scenario is not about missing modalities, but we are trying to provide the possibility of deal with varying input sizes. Very quickly, what we show here is that even in the complete scenario, we present competitive results, and then we try to simulate here the case where we have all the MR and some of the PET images missing, and vice versa. And so what we see is that we do better when the MR is missing. Instead, the traditional baselines, although we remain very close to each other, in some cases they perform better than us. And what we observe is that for certain scenarios, so for instance for MR, a bad reconstruction that might be obtained through one of these baselines really impacts the performance. So in these scenarios, just not attempting to impute the data is better than as we do, is better than trying to provide something. Instead, as PET, we can consider it as a noisier modality. The models are more robust to this scenario. And then again, we are interested in being robust to variations on the equipment that the final users might have. And what we show is that in terms of computation times, our method is way cheaper and then more accessible than standard imputation models using PIX2PIX or cycle GAN. And the second, so I here just very quickly to present the results on breast cancer classification results. Again, we show that we have a very high performance that it's superior in most of the cases to the standard approaches. So we demonstrate that our method is robust to different type of applications. It's very flexible in that sense. So again, here we achieve trustworthiness by being robust to missing modalities. So it means that the models can be used effectively in scenarios that differ from the training scenario. It means if someone does not have a pet in their hospital, they could still use it. We are robust to distribution tricks because, as I said, like imputation might alter the distribution of our data, and this can be very risky. We are robust to the tasks, so we could use this. Our model is task agnostic, so we could be able to use it in any possible scenario. For example, in time series analysis, and it allows the usage of different models. So, like we have our framework is adaptable, and the backbones architecture should be able to be replaced easily without having an important impact in the performance. And finally, again, because it's very important and part of the definition of robustness, we are rigorous in testing, and for this purpose, we have made our code fully open source for others to test it and put it into stress conditions to make sure that it works. So just to finalize and summarize this talk, so as a final insight, so what I wanted to tell you here is that technical robustness is a central element to building trustworthy AI solutions. We consider that by designing robust AI methods, we cover most of the pillars of AI in trustworthiness. We think that indirectly we are contributing to the other 5 remaining pillars. And also, I have tried to show that robustness is an essential element to guarantee health equity, which is the subject of this webinar. And this is on the positive side, but of course, there's also things that remain to be done. So there is great methodological progress that has been seen on the topic over the last years, and this is thanks to the introduction of the term of trustworthy AI and identifying what we were missing to become trustworthy. So I think it's time to deploy and test, which means putting into action the 4th pillar of trustworthiness, which is human agency in oversight. So we are engineers, we love to develop these solutions. Now we need to take these solutions to the final stakeholders and try to interact with them to see if this is what they really need in terms of trustworthiness in the hospitals in different scenarios, and see how we can improve the way that we provide this information to them. And finally, so our vision is that trustworthiness, we can build trustworthiness mostly by focusing on robustness, but it may not be just that. And I'm here showing like a book that we have just finished editing, where many of my colleagues, which I try to give credit here with all of their names, try to address trustworthiness in AI through completely different approaches to the one that I've been trying to present you here, and which are as important and as solid as the idea that we're working on, which is developing trustworthiness through robustness. So there's many ways to reach trustworthiness. It's not just robustness, but trustworthiness, we can get many ways to trustworthiness, I agree, but it's definitely the way to health equity. If we want to achieve health equity, we need to work on trustworthy solutions that provide accessible AI healthcare solutions for everyone. Thank you very much for your attention. This is a work that we've been doing with many people, so I thank all of the students that have been contributing to this work, and I'm happy to answer any questions you might have.
Thank you so much, Dr. Zuluaga, for your wonderful talk and for giving us an overview of the concept of robustness and trustworthy and dive into your technical work. That's great. So I'm wondering if the audience has any questions, they can raise their hands or put your questions in the Q&A box. So we have one question from the Q&A from Feng Yan. She said, very nice presentation, Maria. I missed a little bit about the well-being. Can you explain more about the difference between diversity and well-being? It seems your well-being indicates the equipment shift, which also belongs to the diversity and fairness. Thank you.
Yeah, thanks for the question. So I think diversity specifically, it's more focused on the fact that when we build these models, because we just don't have the capacity to represent everyone that we might be able to represent, we might miss something, like we might be missing some specific groups, but we don't want that, right? So it's how we address this problem. Like we might try to get more data, for instance, but in some cases, this might be difficult. So if we have some of these unrepresented groups, how we make sure that our solutions are fair to them and are not harming them in any way. And well-being is more, I think, more general. It's a more like, I mean, the full title, maybe what is confusing is I didn't pull the full title, is societal and environmental well-being. So I think like, and I think trustworthy AI, it's also beyond healthcare. So societal well-being means we are making AI systems that are beneficial to the society in general. I think in the case of healthcare, it's quite straightforward, right? Like that, of course, we are doing something that is beneficial to everyone. And there I can see like why there's a bit the link with diversity and fairness, because when I say societal well-being, it's for instance, not a very expensive model that will only serve high-income countries, but should be able to help everyone in the world. So there's a bit of diversity there. But there's also the aspect of environmental well-being, which is becoming more central, and first in terms of the resources that might be needed to train all these models. And also in terms, and here it's again like these models are very expensive. We need like extremely expensive computational tools for the equipment to reach that. And it's not everyone has access to that. So it's very, I mean, environmental and societal are again very related in the sense not everyone has these expensive computers. So let's give access to everyone. And also let's make sure these expensive computers might not be in the longer term detrimental for society. I hope this answers the question.
Yeah. Thank you so much, Maria, for clarifying the true scope of diversity and well-being. Maybe we can move to the next question from Chen. Thank you, Maria, for the great talk. Regarding the issue of missing data, I'd like to hear your thoughts on whether generative AI generated content for data imputation is a viable solution, and how can we address the challenge of the hallucination problem?
Thanks for the very interesting question. So I think generative AI, it's indeed a way, I mean, to address data imputation. There is this risk that we are studying of having distribution drift that might have an impact on the data, and that we don't want that, right? We don't want our distributions to be altered. But this is something that we have managed to find a set of rules where we should be able to say, okay, in this scenario you use it, in this scenario you try to avoid it. This is something that could be established. What I think is the big challenge, as Shen like rightly pointed, is the hallucination problem. And I think here something key to address this is what I didn't cover in this talk, which is handling errors. So we need to develop methods that are able to identify situations that they consider, okay, this seems like an hallucination. If we do the parallel on what we see, for example, in social networks, where the people try to detect what is a fake image, what is fake content, we need parallel solutions in healthcare, because it's I mean, something that it's an hallucination might have big impacts in the clinical pipeline. So what we need is systems that are able to detect them and bring them to the attention of the doctor, which is again this thing of transparency and accountability. So it's all linked within the trustworthy AI. What we need to do is to focus on transparency and accountability for this.
Thank you so much. So maybe you can move to the next question. Thank you very much for the insightful talk. In your perspective, what are the most top 3 urgent aspects that academics need to focus in the health AI today?
Wow, that's it's a very difficult question, because I think it's difficult to pick 3. I mean, I think you can see that from different dimensions. I think we need to focus on one side on advancing our knowledge. So it's like very focused research on trying to answer clinical questions for which we don't have answers. So for example, dementia and all these things. So advancing our knowledge, very scientific. I think I would be, but then there will be many sub-questions there, but I think how we use AI to advance our knowledge. Then second, it's how we are able to translate these solutions to use, like for practical use, because again, and this is very related to this aspect of health equity, we might develop very amazing tools that are assisting clinicians in their decisions, but they can be used by a small percentage of the population, right? Like it's resources that are very expensive, and most of the world cannot enjoy them. So it's how we develop methods that are, again, robust, trustworthy, that other people can use it. And then I think the third one is how we make all of this sustainable, because again, we talk about well-being. There's can we really, these things are growing, and can we make solutions that are affordable for everyone and can be sustainable in the long term? I wouldn't say it's like 3 specific questions to answer, but 3 big research lines that I think researchers on healthcare AI should follow.
Yeah, thank you so much, Maria, for the suggestion on high-level ideas. So maybe you can move to the next question. Amazing presentation. Congratulations, Dr. Zuluaga. My question is about bias mitigation in images. What are your thoughts for bias mitigation direct to images when only single sensitive attribute are known and the full multimodal data is not available?
Thanks for the question. Very interesting. It's very challenging, and I mean, I don't think I have the full answer to that today, because that's one of the things we are working right now with our work of missing data. So right now we have focused mostly on the images, but like the next natural step is how to combine other forms of information, which is, as you rightly point to, our sensitive attributes. And we want specifically to figure out how we do this, how, if we don't have all this information, if we can still counterbalance for that. So I still think the way to go, which is very expensive, it's trying to get access to some very few data sets that provide us all this information to start understanding how these are interrelated and how one affects each other. But it's very challenging, because one of the difficulties that we have right now, there's a lot of effort on that, but it's getting these beautiful data sets that we all want to have to answer the research questions that we have, such as this one.
Yeah, I guess working in the health equity domain, always facing such challenging questions that need to conquer in the new frontier. Maybe another question. Thank you for the interesting talk. Have you been working on ultrasound images? Do you have any tips regarding better generalization across different scanners, 2D, 3D, and resolutions?
Thanks. I find this question very interesting, because I mean, I've worked with ultrasound in the past, not right now. I think ultrasound imaging is very challenging for different aspects, and one links to the previous question, which is it's very difficult to get large data sets that allow researchers to really get into them. I think one of the difficulties associated to this is what you're rightly pointing, which is it's very, like, the scanners are very different, the format is very different, and so it's very difficult for things to talk within each other. So right now I think with ultrasound we're a bit lagged on that, just because it's very challenging. I think there's most of the work it's on fetal imaging, but there's for being such a cheap technology, in the sense it's very accessible for people, because having an ultrasound costs nothing compared to having an MR. We don't have the data for addressing that. So the tip that I will have is, let's put some efforts in trying to collect meaningful data regarding different ultrasound applications.
Yeah, thank you very much. I think probably the last question, given the time duration. Thanks for the great presentation. I'm currently in a C for PhD on robustness, and your open slides are a perfect way to dive into this subject. My question is your present results about varying input specification part. Can you develop about the handling error part, like the use uncertainty quantification, XAI, and the current state of the acceptance of AI by clinicians?
So thanks, because like I think you described precisely what it's handling errors about. So what we consider it's an error is, so you observe an output, which means, and if there's an error, it means something went wrong in your model. And what we want is to try to diagnose this through what we can observe, right? Which is the outputs. And so the way we address this, we think this can be addressed is in 3 ways, 2 of which you are listing there. So one is uncertainty quantification. It means my model gives me an output and tells me how sure it is about it. And so we decide if this is something or that can be used or not. We do something that we call quality control, which is a simpler way. It's we have an output and we say this is a good output or a bad output in the simplest terms. And so again, someone will come and do something about it. I mean, the simplest thing is you drop it because you don't want to use it. A more advanced solution to this, which is also you have in uncertainty quantifications, is you will use this information perhaps to feedback your model and improve it for future usage. And the third approach is explainability or interpretability. I have difficulties in finding the boundaries between the 2 terms, which is okay. I have my output. It's up to the clinician to decide if she uses it or not. And the model will provide the elements, which is this explainable, interpretable elements, so that the clinician makes their own judgment in saying we drop it or we don't, because we understand what the model is doing and it makes sense or it doesn't make sense. Current acceptance of AI by clinicians is what I think it's one of the things that I talked in my final insights. I think we have great tools, methodologically speaking. Of course, there's always room for improvement, but I think we are okay right now. And I think what we need right now is to get closer to what within Trustworthy AI we call the stakeholders, because there's clinicians, but there's also the patients or like policymakers, and try to figure out with them if what we are providing is what they really need. Because perhaps, and especially in this aspect of handling errors, we need to figure out on how to deliver the information to the final stakeholders in a way that is meaningful to them.
Thank you so much, Maria, for your great talk and Q&A with the audience. We really appreciate you sharing your knowledge about this field. Thank you so much again for your great talk. And we wish to see you in the future events in the WiM events. Thank you so much.
Thanks again to everyone for attending, and thanks Robu, Weina, and all the women in MICCAI board for the invitation. It was a pleasure to be here with you.
Yeah, thank you so much. Yeah, so another last words, so feel free to join the WiM online community on Slack. And also we have a coming webinar in January 23rd featuring the winners of best paper on the health equity awards. So feel free to join them. We will also send newsletters in January. So thank you so much for all the audience for your attention and your questions. So see you.
And we will also send out a feedback form at the end of the webinar. So if there are topics you want to include in our future webinars, please feel free to include. And then we'll also send a QR code and a link to join Slack in that email to all the Zoom attendees. So you can just click the link to join the Slack, where we can have new announcements there and will be very convenient. Okay, with that, we will conclude our webinar today. Thanks to our speaker, Dr. Zuluaga, and thanks to all the attendees, and thanks to MICCAI community for us to have this opportunity to continue our WiM webinar, which we hope will get more attendees every time and make a larger impact. Thank you. With that, we conclude the webinar, and please welcome to join our next one.